Friction Prelab. Okay, this is what your initial setup is going to look like. You're going to be looking at the friction between the block, which has 3 different surfaces on the different sides, and the back of a whiteboard. Okay, the pulley is clamped to the whiteboard, not to the table, and that's to use, and then you hang the mass off of the pulley string, and that's going to hang over the edge. You must use a short table for this experiment. This won't work on one of the 2 tall lab tables. Okay, here's a close-up kind of what the pulley setup looks like at the edge.
From here, you will move the block so it is entirely on the surface of the back of the whiteboard. Okay? And then you'll come over here and someone will have to measure the height of the mass from the ground. Okay? So you want the base of it, right, the height that is. Alright, and then when you're ready, you'll let go of the block and you'll time how long it takes for that mass to hit the ground.
Okay, here's what the free body diagram of the block looks like when it's on the flat surface. Okay, vertically it's got the normal force and gravity, its weight, and then it's being acted on by tension in one direction and friction in the other direction. I've drawn it this way. That's not how the video was, but depending on how you're looking at your setup, this might be it, or you might just flip the 2 horizontal forces. Either way, tension will be larger than friction because the block does accelerate. Okay, here's the free body diagram for the hanging mass. Okay, tension upwards and its weight down. Here, the weight is going to be more than tension because the entire system is accelerating in that direction. So there's tension in both of those free body diagrams. Do those tensions equal each other? Yes! Alright, the tension has to be the same throughout the string. We assume that the string has no mass in most cases in AP Physics 1. Newton's third law means that the tension on each little bit of string must be equal and opposite the tension on the next little bit. So that means it's constant throughout. So the pulley is just there to change the direction in the string. For now, we're going to assume that pulleys have no mass and that they rotate freely with no friction lost in that rotation. And we have to remember the whole system accelerates at the same rate, right? The string doesn't get more or less slack throughout the process until the weight hits the ground. So the net force on the weight, or in the masses, is the weight minus the tension. They're in opposite directions. If the weight is mass M, okay, tension equals mg minus ma. Here I've chosen the downward direction to be positive because that's the direction the system is accelerating. The net force on the block is the tension minus the friction. Again, I've chosen the tension here to be positive because that's the direction the block is accelerating. If the block is mass capital M, tension equals mass times acceleration plus friction. So since those tensions are the same, I can set them equal. Okay, mg minus ma equals big Ma plus the frictional force. Okay, rearranging that, I get mg minus the frictional force equals big Ma plus little ma, all right, which if I pull the acceleration out of both of those 2 terms, I can simplify. Then solving for A, all right, this is what I get. You'll notice that mg is the total force pulling on the string towards the ground, and the friction is the total force pulling against it, and then you have the combined masses that are being accelerated. Alright, so here's the second setup that you'll use for the next sets of data collection. Alright, you'll have 2 ring stands, and you'll use those with the clamps to put your whiteboard at an angle. Alright, here's an end view look of how the clamps work. You may have one or both of these kinds of clamps in your setup. Okay, this is a lowish ramp. This would be the lower setting, and then you would just move them higher for the next setting. This picture is to show you how you're going to measure the angle on your ramp. So you want a side view like this, and you'll use a protractor to find that angle between the horizontal and the ramp.
With this setup, you'll be looking at how long it takes the block to go up the ramp. So you'll have to measure the distance it travels along the ramp. So here, all right, you're going to, I have a mass holding this down, but you can have a person holding it back. So you're going to time how long it takes for the block to go up the ramp.
Here's what the free body diagram for the block on the ramp looks like. The tension is pulling up along the ramp, and friction is downwards along the ramp because it's moving upwards, so friction always opposes the motion. The normal force is perpendicular to the ramp, and the weight is always downwards. The hanging mass actually hasn't changed which forces are acting on it. So it's still tension upwards and weight downward.